Hi, welcome to Group 6 YouTube presentation on predicting the dispatch of CIT officers based on crisis call data in Seattle. My name is Nushra and presenting with me today is Cameron and Sarah. Just a quick overview of the outline. We'll start with introduction and related studies, then discuss proposed methods, results, limitations, and demonstration to wrap things up. Crisis Intervention Teams, or CITs, are special units of police officers trained to handle mental health crises. They work with highly sensitive and complex situations to help people in crisis and emergency to get the care that they need. Despite the difficulty of the task itself, limited resource and time makes it an even more challenging role. Our project aims to predict CIT dispatch to improve resource allocation and help these teams respond faster and effectively. There are several studies related to CIT dispatch, but using data mining and machine learning model with this field is still growing and limited in scope. Looking at two important studies here, Watson et al. In their work observed how CIT training affects police interactions using regression analysis. They found out that CIT trained officers were more likely to send people to mental health services rather than making an arrest. Ritter et al. Analyzed over 2,000 CIT reports and used logistic and multinomial regression to understand dispatch decisions. These studies lay the foundation for more advanced predictive techniques like the ones we used in our project.
Hello everyone. I will now explain the data we used in this project. We analyzed over 12,000 crisis calls received by the Seattle Police Department. Each records include important detail like the type of the call, the sector it happened in, the officer years of birth, and the age of the officer and their years of experience. It also tells us if force was used or not, and whether a CIT officer, as we mentioned, crisis intervention team officer, was dispatched or not. Our target variable is to predict whether a CIT officer was dispatched or not, which is a yes or no question. One key observation is that about 75% of these calls resulted in dispatch. This means most crisis calls required immediate action. That's all about the overview at this moment. Now let's look at the data analysis technique we used. In this step, we analyze the data to understand its pattern and structure. We use several data mining techniques which are really essential to do in any starting any kind of the project, which is data visualization. In data visualization could help us see pattern and trend. Or another one is association analysis, which showed relation between different variables. And the most important things is anomaly detection, which help us to find unusual data points that also could will call outliers. From our analysis, we found two key results. One, the most call are of the 911 type, meaning emergency call, which means that is really important to consider type of the call, and also officer experience has a right scope distribution. What does it mean? It means most officers have fewer years of experience, but a few have a lot of experience. In next slide, we will learn why this is important, the years of experience, why is important. This analysis help us to go for the preparation of the data. Preparing the data is very important for a clean and accurate analysis. Here's what we did. To handle missing data, we use simple technique. For numeric variable, we use the mean imputation. That means we used the mean to fill the gaps. And for categories like call type, we used the most common value. That means mode imputation. We also treated the outlier, which are extreme value. To treat the outlier, we used the trimming method. We trimmed values above the 99.5 percentile to make the data less extreme. That means, as you see in the figures, that means we only delete 0.05% of the data. And for categorical data, we use factor collapsing, which groups similar together. These steps made the data cleaner and easier to work with the next step. Now I'd like to talk about feature selection in our project. This helps us focus on the most important data and improve our analysis. First, let's understand why we did feature selection. The purpose of feature selection in data mining is to first one is reduce dimensionality. This means we cut down the number of feature or variable we are using. Fewer feature make the model simpler and faster. The other benefit, the other purpose is improve model performance. By keeping only the important feature, we help model make better prediction, and absolutely even for running time it's less expensive to run the model with less variable. So, how we select the important feature? We use technique called feature important analysis with a random forest model. Yes, most of us thinking that random forest is for prediction modeling, but is not only for making prediction. It can also tell us which feature are most important. It does this by measuring how much each feature contribute to the accuracy of the model. After analyzing our data, we found that these features are the most important. First one is call type. This is the type of the call received, like a 911 call or messaging or calling from the normal numbers or something like that. We notice that certain call types are more likely to need a crisis intervention team officer. Also, officer years of experience. This is how many years of officer has been working. Officer with different experience level might be displayed differently. Yes, absolutely. This is depend to the situation and the reason that they called to the CIT team. The other things is use of force indicator. This shows whether force was used in the situation or not. If force might be involved, a CIT officer is more likely to be needed and absolutely might be with more experience. By selecting these key features, we achieved a couple of things. Simplify the model with fewer features, the model is less complex. This makes it run faster and it is easier to understand. Another thing is enhance performance. The model become more accurate because it focuses on the most relevant information. Now, Noshra will start to describe the model that we used. Thank you.
In our project, we used four different machine learning models. Our goal is to predict whether an officer is dispatched using classification methods. We tested GLM to capture linear relationships. We used Mars to explore potential nonlinear patterns, and we used random forest and neural networks to capture complex interactions. These models helps us combine simplicity and complexity to balance interpretability and predictive power. It also helps us handle imbalanced data using a mix of powerful algorithms. We started with generalized linear model to estimate the probability of dispatch. GLM calculates the probability using a logistic function and interprets relationship between predictors and outcomes. Here, P of y equals 1 is the probability of dispatch. The beta values represent the coefficients The beta values are the coefficients that represent how much each predictor influences dispatch decisions. Beta naught is the base level of dispatch when predictors are set to 0. It's also known as the intercept term. X values are the values of predictors for each crisis calls. GLM uses a decision threshold by default. If the probability of dispatch is greater than 0.5, it predicts 1, which means CIT dispatched. Otherwise, it's 0, meaning no dispatch. Our dataset uses 17 predictors, and the extracted coefficients help us understand the relationship between predictor and target variable. If we have a predictor, let's say call type is equal to 911, and if we also have another predictor, officer experience, greater or equal 10, the model will likely try to assign positive weights to the predictors and increase the probability of dispatch. Although GLM is a powerful method, it struggles with multicollinearity and nonlinear interactions. Next, we use random forest, which handles more complexities. Our model is built upon 500 trees, and each tree is trained on a random subset of the original data, which is also known as bootstrap sampling. To further randomize, it selects a subset of predictors at each tree split. This helps avoid overfitting and ensures that the model captures diverse pattern in the data. Random forest uses Gini impurity to decide where to split based on impurity of node. Gini index gives us a measure of how mixed a node is based on the distribution of classes. If Gini is equal to 0, it is a pure node, meaning all samples belong to one class. For example, all are dispatched. Otherwise, it's a mixed node. If we have high impurity, the algorithm splits to reduce the impurity in order to get close to a pure node, and eventually the low impurity tells the algorithm to stop splitting to prevent overfitting. Each tree makes a prediction, and the final result is based on majority of voting. For example, if most trees predict a dispatch, the model will output a dispatch. If you look at the bar plot on the right, it highlights that the date reported and officer arrival are the most influential predictors in random forest model, while features like gender of officer or use of force has lower impact. Neural networks are great at handling large data sets and capturing nonlinear relationships. It is made up of several layers. The layers consist of an input layer, one or more hidden layer, and an output layer. In our model, the input layer consists of 17 predictors, and the hidden layer consists of five hidden layers. The input layer consists of 17 predictors, and the 5 hidden layers, which is defined by the size hyperparameter. Decay is a regularization parameter to prevent overfitting by penalizing large weights. The activation function we used is the logistic sigmoid function, which maps output into probabilities between 0 and 1. The final predictors work similar to GLM. If the probability is above 0.5, the model predicts dispatch, otherwise no dispatch. Mars is a nonlinear regression that's both flexible and interpretable. It breaks predictors into segments and creates basis functions to model relationships. For example, it can capture how officer experience impacts dispatch differently for younger versus older officers. Mars automatically removes unnecessary basis functions. It outputs probabilities which we convert into dispatch predictions. It also strikes a very good balance being able to handle nonlinear patterns better than GLM, but also being more interpretable than random forest or neural network. We use several evaluation metrics such as accuracy, kappa, AUC to evaluate model performance. And from the table, we can see that random forest outperforms all model with the highest accuracy and AUC. Neural network follows with a slightly lower accuracy. Mars and GLM had similar performance, with Mars having a slightly higher AUC. The ROC curve, the ROC plot on the right also confirms these findings, where we can see that the RF curve is closest to the top left, giving the best trade-off between specificity and sensitivity, followed by neural network and then GLM.
So our implementation for this project is split into two separate stages. First, the implementation of our chosen algorithms from scratch, and the implementation of the web app that houses various functionalities using our algorithms. And so we'll touch on the web app later, but for now let's go ahead and take a look at the algorithms we implemented from scratch. Starting with decision trees, we implemented these as a part of Random Forest. So these are a machine learning model that contains internal nodes, branches, and leaf nodes. And so the internal nodes are tests on a feature, branches are a test outcome, and leaf nodes are a final decision or prediction for those tests. And so decision tree predictions will generally follow the flow of decisions from the root node of the tree to a leaf node, where that prediction is assigned a label or value. And our implementation here initializes a decision tree with the specified parameters, and then it runs fit to train the decision tree. Fit will crawl grow tree to split the data recursively, where it will find the features and threshold for each node using best split. And best split uses impurity measures like Gini impurity to make a judgment of how often incorrect labeling occurs, where the best feature and threshold for a node will have the lowest Gini impurity. And so grow tree ends whenever max depth is reached for the tree, or we fall below the specified number of samples in a split. And once we have this model trained, we can run predict on the model to traverse the tree with a given value until we reach a leaf node and get a prediction. Random Forest itself is a machine learning model that avoids issues with overfitting that those decision trees suffer from by training and aggregating multiple decision trees. And so each tree is trained on a bootstrap sample, which is a random sample with replacement of the data set. And so the final prediction for a random forest is determined by a majority vote of those decision trees, where the prediction that occurs the most is what gets chosen. And so our implementation here initializes a specified number of decision trees with a specified range of parameters, and then it runs fit to train them. And so this actually calls fit, like the fit function from the decision tree algorithm, on each decision tree. And then once the trees are all trained, we run predict, which also calls the predict function from the decision tree algorithm on each decision tree to aggregate a list of predictions made by the decision trees, and then make a final prediction for random forest based on those. Neural network is our other model, and so this is a model inspired by networks in the human brain of the same name. And so these are made of several layers of nodes. The input layer, which receives input data, one or more hidden layers, which process data from the input layer by using each layer's neurons to identify complex relationships in the data, and then an output layer, which makes the final prediction. Layers are connected with a weight value, and each neuron has a bias value used for adjusting its output. And so the data will pass through the layers to compute the final output of the network during a process called forward propagation. And so whenever we have that final output, the network will adjust the weights of the layers during a process called back propagation to tune the model and then minimize the difference between the final output and target value over each epoch. And so our implementation initializes a neural network with the specified sizes for the input, hidden, and output layers, as well as a learning rate for controlling the frequency of updates to the weights. And so we can run fit here once it's initialized to call forward propagation, back propagation, and cost, those three functions, over a specified number of epochs to train the neural network an equal number of times to the number of epochs specified. And so once the neural network is trained, we can run predict to run a given value through forward propagation in the neural network. And then during that process, the value will be squished into a number between 0 and 1 that we can use to make a binary classification based on whether said value will go ahead and fall above or below 0.5. And so with these algorithms implemented, we want to go ahead and train the models and use them in the web app. We do this by calling those files for Random Forest Neural Network through our test bench files here. And these files will import the data set, format it into an acceptable input for our algorithms. Then it will train our models and then save and export those models as PKL files. And so those models get imported into the back end of our web app, and they're used to make predictions during the use of our web app's functionalities, as well as highlight certain metrics. And so our web app is constructed using Flask. The back end is written in Python, and the front end is written in HTML. And so our back end contains route functions for each of the pages that the user can access, as well as some convenience functions for handling the models and data. And so we load in our PKL files for the trained models at runtime. And whenever the user interacts with the page, the front end will send requests to the back end that will execute the appropriate logic in the relevant route function. Our front end uses an HTML file for each page of the web app. And so each file houses and organizes the content and interactables of the page. The user will start in the home page, which is named index.html. And then they will access each of our functionalities through subsequent pages. And so we have our upload functionality, which will accept a dataset file and append it to the existing dataset we use. And also, this page has an option to toggle model retraining after appending that dataset. We have batch prediction functionality, and so that displays for a specified model its predictions as well as the actual result for every entry in the current dataset. We have a single prediction functionality, which will accept values for a series of features and then makes a prediction using the specified model. Then we have a data visualization functionality, which will display visualizations for the characteristics of the current dataset. And then we have a model comparison functionality, which displays visualizations that compare the metrics and results of the implemented models. And so these are some results shown in the model comparison functionality for the versions of our models trained, just the single version trained on the clean data set without any independent entries. And so our neural network model is superior by far to our random forest model in accuracy, precision, and F1 score. But our random forest model is superior in recall. We also have confusion matrices for our models here, which show for each model how many correct and incorrect, positive and negative predictions were made. So these matrices actually lined up pretty nicely with our results in the previous slide, because we see that random forest does make more positive predictions than the neural network model, and it has higher recall as a result, but it also has an incredibly high amount of false positive predictions, and so that indicates lower values for accuracy, precision, and F1 score. So what are our takeaways? Well, first, we definitely believe that our models had rather varied performance. Neural network was good, but random forest struggled quite a bit. In fact, we ourselves struggled quite a bit with implementing random forest behind the scenes. So the model's issues could very well stem from that, stem from those unresolved issues we had during troubleshooting. And so as a result, we could probably we could really stand to tune random forest quite a bit more, just to try and fix some of those issues and make it get anywhere close really to the accuracy of neural network. But we could also try and implement other models like GLM and Mars, which we mentioned earlier, maybe even other variants of the random forest neural network models, or models that maybe we haven't really discussed in this presentation and haven't come across yet. As far as the web application, we believe it could prove to be pretty useful in the real world, as it could help with CIT dispatch predictions, but it also has more functionalities than just predictions. The data visualization stuff in particular in the comparison visualizations could help users understand which model would be best for a given situation. But if we or someone else were to pick this work up in the future, what we've done here will stand to help quite a bit with modeling CIT data or other similar data sets that will deal with classification, especially if it is using a model anywhere close to random forest neural network. But that concludes our presentation, although before we go, let's go ahead and show off our web app. So first, we're going to go ahead and run Python app.py to start our backend. And so then we will navigate to the web page for our front end. And so we can go ahead and see all our predictions, or we can see all our functionalities rather here. And so we can start with uploading a data set. We'll just upload an identical version of our data set. We're not going to retrain it just because that takes especially long. I'm talking like 25 plus minutes sometimes. But we will run batch prediction. Let's do this with random forest. So this will take a moment. And it may be pretty high load. In fact, it might even crash, depending on how big the data set will be after adding an entire version of itself to itself. But we can just see that for maybe the first 50 results, which this goes up to the tens of thousands, that it makes predictions, and then it will show the actual predictions. So some of these are correct, some of these are incorrect. But if we go back to home, we can show our single predictions off. So we can just put values in here. We can give the officer a year of birth 4, -2 years of experience, no CIT certified indicator, a call type of 911, officer race, 2 or more races, female, sector Edward, use of force indicator yes, and we'll do neural network. So this predicts that a CIT officer will be dispatched, and you can get both yes and no predictions here. And then if we look at our data visualizations functionality, we see just a couple of visualizations we have for our models in our data set. And so we see that we have a distribution of officer race visualization and a visualization for the distribution of whether or not CIT officers were dispatched in cases where use of force was or was not indicated. And then finally, we can show off our visualizations for the comparison of the models. And so this takes slightly longer because it's having to run backend code on those models to pull up this information, which is dynamic and dependent on the current version of the model. And so as you can see here, it is actually slightly different from what was seen in the presentation, and that's a result of appending those data sets. And so if we look here, we can see we have the same performance metrics table. We have our confusion matrices. There's also this comparison plot that is basically just a plot version of this table. But that shows off all of our functionalities, and that concludes our presentation and demo. Thank you.